here?
Yep.
All right. Hello, everyone. I'm Gielen from IBM Research in the United States, and I'm also the president of the IEEE CEDA. So I'd like to welcome everyone to Tuesday day keynote luncheon talk. This one is particularly sponsored by IEEE CEDA. Before we get into the main event, I hope everyone and your family is well and safe. Also, I really appreciate your efforts to attend in this event, particularly those folks in the conference site in person. I don't know, it has been more than like 2 years, and I think a virtual conference became a sort of the norm nowadays. However, I hope we'll get back to more in-person conference soon. Since this is a CEDA-sponsored event, let me briefly introduce IEEE CEDA first in 1 minute. The CEDA stands for the Council on Electronic Design Automation. It's a council formed around these the member societies: APS, Antennas and Propagation; CAS, Circuits and Systems; CS, Computer Society; EDS, Electron Device Society; MTTS, Microwave Theory and Technique Society; SSCS, Solid State Circuit Society; EPS, Electronics Packaging Society. And the vision is to become a provider of information and community service in design automation of electronic and embedded systems. So for more detailed information, please visit CEDA website up there. And if you're not already, please join the membership from there. So with that, today, I'm extremely pleased to introduce Professor George Gielen from University of Leuven, Belgium. Professor Gielen received the MSc and PhD degrees in electrical engineering from the Catholic University Leuven, Belgium in '86 and '90, respectively. He currently is a full professor in the MICAS Research Division at the Department of Electrical Engineering at KU Leuven. He was a visiting professor in UC Berkeley and Stanford University. And since 2020, he is chair of the Department of Electrical Engineering. His research interests are in the design of analog and mixed signal integrated circuits, and especially in analog and mixed signal CAD tools and design automation. He has co-authored 10 books and more than 600 papers in edited books, international journals, and conference proceedings. He's a 1997 laureate of the Belgian Royal Academy of Sciences, Literature and Arts in the discipline of engineering. He's a fellow of the IEEE since 2022 and received the IEEE CAS Mac-Ben Valkenburg Award in 2015 and the IEEE CAS Charles Desor Award in 2020. He's an elected member of the Académie Européenne. So without further ado, let me hand over the podium and mic to Professor Gielen here.
Thank you. Gielen?
Yes. I'm gonna stop sharing here.
Yes.
Yeah, okay.
Okay, thank you very much, Gielen. Welcome everyone, wherever you are. Welcome also here, people in the audience here in Leuven. I'm very pleased to be able to give this luncheon talk about AI in the edge of AI. Just before starting the actual talk, a quick wrap up. I'm a full professor here in the Maika's group in the Department of Electrical Engineering at the University in Leuven. This is a big group with 6 professors and about 80 PhD researchers. And we cover all aspects of nanoelectronic IC research, from analog, digital, RF, millimeter wave to AI and machine learning chips. Personally, my expertise in analog and mixed signal IC design and CAD, and that includes AI techniques for analog mixed signal design automation and test. And one of my flagship projects is my ERC Advanced Grant Analog Create, where we are using these AI techniques for analog IC design automation. Here is the summary of the presentation. First, some brief motivation. Then the smart sensing front ends and how we can address those. Then some words about edge AI accelerators, learning in the edge, and I will wrap up with some conclusions. Let's start with the motivation. In the world of cloud computing, you have lots of servers that do all the processing in the cloud. They get the data through the edge nodes coming from the individual edge devices. And so, some of these are smartphones and laptops and so on. But more and more in the realm of Internet of Things, these edge devices can be ordinary objects, can be ordinary appliances, cameras, etc. Here you see some market data about this Internet of Things explosion. At the bottom left, you see the number of connected devices, which really explodes into the billions, tens of billions, forecasting even by 2025, 75 billion devices connected to the internet. And that, of course, results in a big market that by 2020 was estimated to be about $400 billion. And that in particularly has growth rates that are spectacular, 30 to 40% of growth rate. If you want to see the driving applications, then the major ones are smart cities, industrial IoT, connected health, and smart homes. Now, with this huge increase in connected devices, we of course get lots of data that need to be transmitted through the internet to these cloud servers. And with that exponential growth, this becomes impossible to do. It requires huge amounts of power to transmit the data. The bandwidth and the processing capabilities are limited. And also transmitting all those data and getting results back has high latency, which is not always acceptable. And that is why there is an increasing motivation to move the processing closer to the source of the data. So to do more local processing and real-time analytics in the edge devices and in the edge nodes. And that is exactly what we call edge computing. Now, once you do the local computing, you can also add intelligence there by adding AI and machine learning algorithms and embed them in those edge devices. And when you do so, of course, you get a reduced latency in the system because you do everything locally. You save network bandwidth because maybe fewer data need to be transmitted. Your system power consumption for the overall system reduces. You also do not depend or depend less on the network, whether it's available or not available. And of course, you do not transmit all those data through the internet, so it's more secure from a privacy point of view. This market of edge computing is therefore also growing, and McKinsey estimated that by 2025, this edge computing market is around $200 billion. Here are some of the driving applications for our research in edge computing. First of all, we have the biomedical applications where you can use all kinds of wearables to do monitoring and healthcare control for individual persons. You can have advanced human-machine interfacing, for instance, touchless gesture recognition to operate devices like in a car. You have virtual augmented reality, and you also have autonomous navigation, like for instance, drones that hover around and deliver packets. Now, if we look at the architecture for such an edge device that is physically connected to the world with some sensors, we have the sensing units where the data are read out and then converted into digital. So we call that the sensor readout. Then in such edge device, we have to do some local processing. So that requires some processors in the device. There is a local user interface for interaction. There's local memory. So that's the embedded edge processing. And then of course we need some part for the communication to the internet. And of course we need a block that provides the power or the energy of the device. I will not talk about communication and the powering of these edge devices, but in this talk, I will focus on the two other aspects, the front end and the edge processing. Starting with the front end in an edge device, what we notice is that you can sample signals at a data rate and create lots of data. However, if you look at the actual information content that is present in those data, it is often much smaller. So in other words, the information rate can be a lot lower than the actual signal bandwidth. And that is precisely offers the opportunity to exploit those characteristics of the signal in order to save energy without destroying information fidelity. So keep the same information content, but have less data, only information. That depends, of course, on the application. And I show you here some biomedical signals, ECG, EMG, action potentials, and EEG signals. And for instance, if we look at the ECG signal, there you can see that the information that is relevant to estimate the correct heartbeat behavior is rather in the peaks and the repetition rates of the ECG signal. And if we look, for instance, at the action potentials, then you can see that there is little information in the signals in between spikes. And so you can say that the actual relevant signal is very sparse in time. And so the clue is, how can we exploit these features of the signals to build edge front ends, that edge device front ends, with less power consumption. One way to do this is to use compressed sensing. In the technique of compressed sensing, we map the incoming signals to a lower dimensional information space. Since it's lower dimensional, it has less data that we need to transmit, and so on. If we transmit them, they can be reconstructed on the receive side. And for instance, the group of David Atienza in EPFL has been exploring this on biosignals, in particular when applying the discrete wavelet transform on ECG signals. They have found that the result is highly sparse. And if you even do an additional thresholding to remove coefficients below a given value, then they showed that with only 8% of the original sensed data, you can reach, you can reconstruct the signal after receiving it and reach full signal fidelity. So you don't lose information and you get a lot of power savings. Another possibility is to do an event-driven readout. So as you see from the figures there, instead of sampling and converting signals at fixed Nyquist rate, we can exploit the fact that a signal has a low activity and only sample the signal when it changes significantly. So this is a scheme that you can call event-driven because it's fully adaptive depending on the signal activity itself. Now, one implementation for this is a level crossing A to D converter, of which one possible architecture is shown here. So the DAC, the DAC that is there, indicates the current level of the signal. And then you compare with the comparator up and below, you compare whether the signal increases in a positive or a negative sense with more than 1 LSB. And in case it does, you can generate a signal at the output, both in amplitude and time. So in this way, you can create, for instance, asynchronous spiking signals at the moments of the level crossings. Jona van Asse has implemented this system, and he has analyzed that this gives you savings at the level of the A to D conversion itself. We compare to the most power or energy efficient A to D converter that is used in practice today, which is the SAR, successive approximation A to D converter. And as you can see from the graph, if the required signal to error ratio, which is a generalization of the SNR, is not too high, then the level crossing ADC has a big power advantage. That's at the level of the ADC itself. But of course, since at the end you have less data coming out from the level crossing ADC, you also have a big advantage at system level, which of course depends on the type of signals. So it depends on the application. And here again, for the 4 biomedical applications, you see that Nyquist rate sampling with the SAR is the blue block here. And then the yellow indicates the power consumption for the same signals in a level crossing ADC. And you see that you get 1-2 orders of magnitude power savings by doing this method. Now, it's not always easy to find out which technique you have to use in terms of front-end optimization, and that's why we have developed a pathfinding, an architectural pathfinding method, Omniscent, for energy-constrained sensing applications. It is built on accurate power estimation models at architectural level, and it allows the designer to explore different alternative architectures for the front end in Simulink. So while doing Simulink level architecture exploration. An example is shown here. This is the investigation of introducing a compressive sensing encoder, not after the A to D converter, but in the analog domain before the A to D converter. And you can see here that doing this for the application that we had here, I think it was a epileptic signal detection, that you see that you get an order of magnitude power advantage. For those who are interested to get more details about this, I refer to Thursday, where this paper is being presented in the conference program of date 2022 itself. That's to generate the data. Then we move to the local processing with AI devices. So we get the data and we try to extract features and do an interpretation of these features in a neural network. For instance, assume that you have an application where you have as input images. The idea is not to transmit pixels. The idea is to interpret locally in the edge device the picture to recognize, for instance, objects, persons, statues, lanterns, etc. And then, if needed, transmit only that information. Doing that object recognition typically is done in a deep neural network with training that is done offline with some kind of backpropagation rule, and then with some online inferencing to apply it in the field. And to do that, you need fast multiply, accumulate, and local storage. Now, depending on the task that you have to do, that requires a certain computational complexity. And for instance, if your task is simple, like recognizing one wake-up word or a limited vocabulary of 10 words, this might be possible to do in the edge with real-time CPU or so. But if you go to really advanced tasks, such as shown here, where you have a speech accent interpretation, then the CPU will take too much power to do this, and you need to have machine learning accelerators to be able to do this in a way that is compatible with an edge AI device. So the question then is, okay, which processing architecture is then the most suited for a given application? And of course, choosing that as a trade-off between the speed, the performance that you need, the power consumption, the chip area and cost, latency, and flexibility. So let us look at the state of the art of machine learning accelerators, which is this graph. And for the interested people, I refer to this website where you find all these data nicely available. The graph shows the power consumption of the published and reported devices on the x-axis, and on the y-axis you see the speed in billion operations per second. You see that there are many dots, and you have these dashed lines of constant energy per operation. So you can implement these AI algorithms in a CPU, but that would cost you a lot of power. You can implement them in FPGAs. That still costs you a lot of power, as shown here by the blue dots. And of course, in order to reduce the power and even crank up the performance, you need these purple blocks here, which are digital accelerators. And if you want to improve the energy efficiency even further, then you need to move to these yellow dots here, which are analog mixed signal accelerators. So the clue to have the artificial intelligence signal interpretation done in an edge device is that you find architectures where the energy consumption, the joules per operation, go down, and where the operations that you can crank out of a square millimeter of silicon area increases. And one way to get there is to do really a co-optimization of the algorithm and the architecture. Now, I told you that the analog accelerators may be more energy efficient, but they have more restricted flexibility compared to the digital accelerators. And that is why Kodai, in the group of my colleague Marianne Verelst, here in the University in Leuven, has recently, actually a couple of weeks ago at ISCC 2022, presented a chip where you combine actually an analog and a digital accelerator in one and the same chip. So the digital AI core is then characterized by a high bit precision and can address fully connected layers and has a lot of flexibility, while the analog in-memory core has a lower bit precision, but can address massively parallel layers, be it at limited flexibility. And of course, you can then add a CPU to do other tasks such as pre-processing, high-level control, external I/O, and so on. And so the nice thing in their work is that they combine all these three things within one and the same chip. You see the block diagram here. The digital core consists of a 16 by 16 processing element array. And the analog, and it has a max pooling. And then the analog core has 1152 times 512. array and the SIMD block. And they both share L1 activation memory. The two blocks then also share the memory with the CPU, which is a RISC-V processor that is also embedded on the same chip. Now, why is this interesting? Because you can now do an end-to-end mapping of a certain workload onto this device and map. Typically, this workload depends on different layers, and you can map individual layers onto either the digital core or onto the analog core, depending on the characteristics of that layer and where it fits in the most energy efficient way. Typically, the input layer would be mapped on the digital core, while intermediate layers are mapped on the analog core. And again, the output layer is then on the digital core again. So in this way, you can get a very power efficient implementation of a given AI algorithm. Some more details about their single chip. The digital core has weights of 8 bits. The analog core is 2 bits. And in terms of performance, the efficiency of the digital is 2.18 tera operations per second per watt. And the analog core has 208 tera operations per second per watt. This is at power supply of 0.8 volt. But of course, the device, as you can see, the device can also operate at other supply voltages. Now, in order to know what is now the best architecture for a given workload application, Professor Van Helst and her group have developed the zigzag exploration environment that allows to optimize deep neural nets, starting from, so it's based on cost models for energy consumption, the latency of a specific hardware solution, and the area, the chip area that it costs. And starting from the workload of the neural network that is targeted, adding hardware constraints resulting from the architecture, memory hierarchy, and so on, and technology constraints in a specific technology. Different mappings can be applied to the workload in order to define spatial and temporal rollings, etc. And all these different alternative architectures that result from this are then calculated in terms of energy, latency, and area. And then you get the result as shown here on the graph. So these are the different possible solutions. And this is then the chip area, the time needed for inferencing in every solution, and the energy needed for inferencing in every solution. And after this exploration, the designer can then pick the desired device, the desired solution for his or her specific application. People who want to know more about the zigzag tool, it's available on this GitHub site. Now, this is still a deep neural network. In the edge, of course, we want simple complexity. And that's why there is one alternative to traditional deep neural nets, and that is the use of spiking neural nets. They are based on biological neural networks, and the whole idea is that they will result in lower hardware complexity, therefore less power and area. The devices that we typically use are integrate and fire and leaky integrate and fire spiking neural models. Now, in our case, we have been applying this spiking neural network model to the application of gesture recognition from radar data. Radar, because that's very robust in all kinds of environmental conditions. and different groups around the world are active in this area. Companies like Google, Infineon, and universities like Leuven, IMEC, and University in Antwerp. Here is the spiking neural net that we have been using. It has 3 spiking neural layers here, and it uses 4 bit weights, so very low complexity. But we found that just with the spiking neural net, we do not get good performance. In order to get good performance, classification performance for the gestures, we need to have pre-processing in front of the spiking neural net. And after some optimization, we found that this was the best pre-processing for the radar data. So we first do a range processing, followed by a short-term Fourier transform to get microdoppler data. Then we do band limiting and soft thresholding, and then we do a spike encoding and send that to the spiking neural net that is shown at the bottom, that then does the classification of the gesture. Here you see that with the spiking neural net, and after optimizing the different pre-processing steps, we get a classification performance of 89%, which compared to a trained deep neural network, 93% is quite good. And with some further optimization of the spike encoding, in particular, the use of time to first spike encoding rather than rate-based encoding, we were even able to crank up the classification accuracy to 93%, which is comparable to the deep neural net. So this really was encouraging to say spiking neural nets have a lower complexity than the deep neural nets and can have comparable classification performance than the deep neural ones. So they might be very interesting for edge AI, edge devices. We also found we applied this to other data sets like the 11 class Google Soli class, and the results were very comparable. Please look up the papers of Ali Safa to know those details. And also important to know is that the estimated energy per inference is 2 microjoule on the microbrain architecture. And this microbrain architecture is one of the 4 architectures that currently have been or are being designed in IMEC. So they range from very simple low power devices to larger devices with arrays of tiles. This has then also been combined together with the analog to spike level crossing front end, the microbrain architecture, and a low power wireless communication link in a cardiac monitoring application, resulting in a power consumption that is much lower than if we were to use cloud, pure cloud application. The last thing I want to say is the learning. So with these edge devices, we also want to do local learning. And here I want to point out a couple of recently presented approaches. The first one is the Recon approach, developed by Charlotte Frenkel, who is currently at ETH, and also presented at ISCCC a couple of weeks ago, where the whole challenge is to do the on-chip learning over data that have a time scale of seconds. The traditional way to do that is to use back propagation through time, but this will result in a huge memory overhead. And therefore, she developed a solution that is based on the bio-inspired EPROP learning rule, where you have learning signals that depend only on the current time, and you have eligibility traces that look forward a short period in time. And then you can have a good learning results with a memory overhead that is only 0.8%. This is the result from the chip that she presented at the conference. And here you see the data from the different applications that she demonstrated there. Some vision data with gesture recognition, 87.3%, auditive data for digit recognition 90.7%, and then navigation example 96.4%. And you find here all the power numbers running down to 20 microwatt for inferencing and 46 microwatt for learning. So these are typically numbers that can be executed in the edge. Another learning application that does not require supervised learning is one we developed here in Leuven and IMEC, is the use spiking neural nets in combination with spike timing dependent plasticity, or STDP. In this case, you do not need any access to the internet, and the network itself, as shown here, has a recurrent structure, and when it evolves over time, it learns itself and it converges to the solution of this optimization problem here, where the reprojection error is minimized, and the output is then suitable to do nice classification. We showed this on the results from a DVS event-driven camera, and you see here that comparable to other solutions of the same complexity as our SNN with STDP, we have a very high classification accuracy. And if you compare it to deep neural network solutions like ResNet and CNNs shown here, then we have a good accuracy. The others are, of course, slightly better, but they are much more complex and require this huge offsite training. Here you see how the network evolves. So starting from scratch, nothing pre-learned, nothing pre-decided, it learns itself. And we stop the learning when the inner loss function stabilizes. A last thing that we did is to use continual learning. In this case, we apply this to a drone that we learn to recognize objects in a room, recognize persons. So here we combine our SNN-STDP framework that I just explained. We use that in a convolutional setting. During a very short time period, let's say 2 minutes, we combine it with the data from an oracle, in this case a YOLO network. And after that, the network has been trained and can be, the device has been trained and can be used to guide the drone around. Obviously, the trained SNN in this case, again, has lower complexity, so less power and area. And this is how it works. With 2 SNN-STDP networks in convolutional setup at the input to process the event camera data, and at the output to create the attention maps. And we need 2 regularization steps in between. And here you see how it works. So the attention maps indicate that there is an object, in this case a walking person, detected in the images. And in this way, the drone, when flying, can avoid these persons. If we were to compare this to a deep neural net that would have much higher complexity, 5 instead of 2 layers, and that would be trained offline, you see here in the precision recall plot that the offline SqueezeNet with network with RGB data has maybe a slightly better performance for RGB data, but for the DVS camera data, our spiking neural network approach does a lot better than the more complex SqueezeNet approach. Yeah, so this brings me to the conclusion that edge computing is a necessity in this growing world of connected devices, and that you can work on the smart sensing front ends, where the key is to focus on getting the information rather than getting data through all kinds of techniques. and that you can do power efficient edge AI acceleration, optimizing hardware and algorithm. Question is, do you need to spike or not a spike? And we try to embed learning efficiently in the edge. And I have to thank all my researchers, collaborators, and funding agencies, and I'm ready to answer any questions.
Okay. Okay. Okay, thank you, Joe.
Marian, do you have any question from on-site?
Yeah, we have, but we're fixing the. Okay, we are here. Yeah, so thank you, George, for the interesting talk. We have a couple of questions from online, and then we might have more from the room. The first one is from Ian O'Connor, and he says, excellent talk, George. Extracting the best from analog and digital is certainly a very important way forward for energy efficient edge intelligence. But how do you see co-integration issues? Would the analog and digital part be implemented in the same technology or not? What about packaging, 3D integration? What are your views on that? And in light of the intensity of the communication between analog and digital?
Yeah, thank you, Ian. A very good question indeed. The co-optimization of the analog part and the digital part may lead to system optimizations beyond what is possible if you optimize analog and digital separately. And I showed you here in the results 2 exploration environments, one from Jona, one from the zigzag environment. It would be nice if things could be combined and get a more system level perspective. On the other hand, when we talk about implementation, and the question is whether this should be done in one single chip, or whether it's better to have this in 2 chips, that needs to be seen, because often making the analog circuits in the advanced technologies is much more challenging than just putting everything on the same chip.
Okay, thank you. A question from Ilya Polyan is that many applications you mentioned are safety critical, yet classification accuracy is around 95% or less. So 5% misclassification, is it important? And for safety integrity level requirements, can we still improve accuracy because it might not be good enough?
Well, we try continuously to improve the quality of these algorithms, but it would be not wise to assume that we will ever get 100% classification accuracy. So the answer to that is probably very similar as in our brain, is that we need multi-data, multi-sensor fusion to get different input sources and combine the information from those sources to get a conclusion that has a much higher accuracy than every individual sensor by itself.
Okay, I'm also looking whether we have any questions from the room here. And waiting for that, let's take a last one from the chat. So on slide 19, you mentioned machine learning accelerators and their performance was expressed in operations per second. And Smail asks whether you consider machine learning operations as a conventional operation, or we should not better start to talk about frames per second or some inference speed metrics instead of just normal addition and multiplications.
Yeah, that's maybe correct. That depends a bit on the application. But I also reported some power per inference numbers throughout the presentation. That's correct.
Okay, any more questions here or any questions further online?
I have one question.
Not, I think, oh, yes.
You
have the microphone of.
So, first of all, thanks very much for very interesting talk, Professor Gielen. You're approaching this from the edge computing perspective. in my case, I'm the other end of spectrum, which is like data center architecture, cloud architecture, computation fabrics.
You must be working for IBM, I guess.
Yeah, that's right. And as a matter of fact, the other day when we had an internal discussion, like what would be the ideal, computation fabrics and architecture for the data center. One of the block diagram is kind of similar to what you presented in the data, the accelerator domain, like with the RISC-V and some of the DNN accelerator, this kind of things. So my question is, even for the edge computing devices, do you envision that these DNN or CNN types of accelerator will be part of that edge computing devices, or do you think that it's more like a sensing or collecting the data from the area and then send the signal to the data center, have a computation done in the cloud and coming back?
Well, no, I think there is certainly a mixture of applications possible. In the sense that some applications where you have the nice link and where you have the bandwidth, that it's much better to transmit the data to the cloud and do the processing there. But in other applications, the link might not be there, or the device needs some local autonomy. And in that case, the device must be able to control itself, to take local decisions and so on. And in those cases, it's better to have local embedded processing. So I don't think it's either one or the other. I think there will be applications doing this and other applications doing that.
Okay, thank you. Okay, Marian, do you have any other question from the site?
No, we have.
And I think we covered all the questions from the chat boxes as well.
Let's see.
Because the last one is about the accuracy you already covered, right? Okay. And I think this concludes our keynote session on Tuesday. Once again, I'd like to thank Professor Gielen for a wonderful talk. And also, I'd like to thank all the audience in this session. At some point of time, it went over 80, which was a great attendance. So thanks very much, everyone, and see you next time. Thank you.